All right, everybody, good morning. And welcome to Renew Breakfast and Learn series with the Office of Sustainability. I'm Teddy Lutelier, Sustainability Manager for UM. I'll be your host today. And today will be a session dedicated to sustainable home design. And we'll have our dear Professor Trussoni presenting. I'll introduce you to Matt in a second. I just want to go over a few housekeeping rules, very simple. This webinar is going to be recorded, so you have a chance to actually share it later on. We'll send you a reminder. And also, if you have questions, you can ask them whenever during the session. The only thing is you cannot use the chat, is deactivated, but you can use the Q&A. So use the Q&A when you have a question, and at the end, we'll have 10 minutes to go over those questions with Matthew. So with that, I want to introduce Dr. Trussoni. Is a practitioner and professor of engineering and architecture. He's a professional engineer, a registered architect, and certified general contractor in the state of Florida. He currently is an assistant professor in practice at the University of Miami College of Engineering. He has also taught at the Milwaukee School of Engineering. He owns and operates Trussoni Architect Group and Trulin Construction LLC in Miami. He received his Bachelor's of Science in Architectural Engineering from Milwaukee School of Engineering in 2003. And he went on to receive a dual master's degree in Architecture and Urban Design in 2005 and a PhD in Civil Structural Engineering in 2009 from the University of Miami. So with that, Matthew, welcome.
Great. Thank you, Teddy. Thank you for having me. Special thanks to the Green U and the Office of Sustainability for putting on this series. Really excited today to talk to you guys about a house that I designed and built here in Miami, Florida. And we're going to take a look at the different sustainability measures and resilience measures and things that we incorporated into the house. You can see the back of the house here. You know, it looks like a pretty normal contemporary house that, that you would build around Miami. Thank you for the great introduction. And I'd just like to say that this, this presentation was based on a presentation that I gave previously for the Florida Engineering Society for PDHs or continuing education. So there's going to be a little bit of education in it for the Learn with the Green U in the morning for breakfast. So why don't we get started? So our agenda, well, it looks like we're going to go over our objectives that we're going to get out of the presentation, and we're going to talk about how it's organized. It's organized a little bit uniquely, kind of along the procurement process, but we'll take a look at that. We'll talk about the impetus for all these changes in the built environment, right, which we're going to show through a single family home, but they apply to the industry in a broader context as well. And then we're going to talk about the implementation of the resilience and the sustainability measures for residential projects in particularly, and taking a look at it through the purview of a single family home here in Miami, Florida. So our objectives, right, at the end of this presentation, you guys should be able to talk about sea level rise, temperature increases, hurricane frequency and intensity increases, define resilience and sustainability, categories as pertaining to finished floor elevation, the structural shell, the envelope and insulation, water reduction measures, right, water production measures, they're harvesting is what we call it. Energy reduction and energy production, and then apply those to a single family home. And so just to kind of set the table a little bit, I want to start with a video from the mayor of Mexico Beach, Florida.
We just had the most amazing family vacation. Let's go! Oh my God!
80% of our city was destroyed, so if you look at it just statistically, we hadn't done much, but yet we've done a lot. You know, I knew things weren't going to move real fast, but our local people are just overwhelmed, Bo. I mean, hell, they can't handle this. Have our paddle in the water a long time. And that's, I mean, we lost it all. We lost our police building, our fire building, our civic center, our water tank, our pier. Wrote it, no. That was on your desk, man. We've wrapped our arms around our citizens and said, hey, let us help you with this. And we're not changing a whole lot of things. I mean, we're not going to allow big money to move in here and change our character and our charm. You know, we're not going to build taller. We don't need to be big and tall and bright lights. Just know if your number's called that sometimes you just pay the price.
So, you know, his final words there, you pay the price. You know, I want you to remember that, and we'll come back to that a little bit towards the end of the presentation. So the way that I organize the presentation is really around the procurement process of, you know, delivering projects in the architecture, engineering, and construction industry. Starts with like discovery and design, right? So that's kind of the beginning stages where you collect all the information and then design the building. And then it goes into engineering and permitting, right? Doing kind of construction documents, the calculation packets and things, and going to the building department, getting everything double checked, making sure it's up to code, and then construction and operation. And so, you know, that's where the rubber hits the road, where you're actually building the building and then operating the building and doing some metrics around it to make sure that it's performing the way that it should. And you're going to see when I get into each one of the topics, it's going to be organized around this kind of this way. And the reason why we did that is because it really outlines how we deliver projects in a sustainable fashion. On the bottom side of the graph, we have kind of design at the beginning, the construction document engineering in the middle, and then the construction operation at the end. And what we really are aiming to do is we're trying to push the decisions, the important decisions that we make towards the beginning of the design process. That allows us to have more control over implementing those decisions, those sustainability and resilience decisions, and controlling the cost of those decisions during the procurement process. And so really what we want to do is we want to have a larger impact on those projects as far as resilience and sustainability, and using certain things and certain methods helps us. And one of those methods is called the integrated project delivery, which is a method that fully integrates project teams in order to take advantage of the knowledge of all the team members and maximize the project outcomes. And so if I go back for a second, you know, using that IDP pushes that curve back where we want it from the traditional design process. We also use building information modeling, which is a computer tool. Basically what it is, for those you don't know, you build a 3D model of your project in the computer, and then you attach a bunch of information to it. And that information is really the key difference between a traditional CAD or AutoCAD program and building information modeling, is that we can attach all kinds of information to our elements, and we can do analysis with those elements. And I'll show you, we'll do some of the energy modeling and some of the other stuff that we do in order to have predictive capabilities, in order to predict how that building is going to perform before we actually build it. And so why are we doing all this? Why are we changing? Why is the building environment changing? Really, well, because the climate's changing. And we can see that here, you know, pretty clear as day. If we look at temperature change since 1850, we can kind of see where it starts to change and then really starts to change around 1980. We've had about 1 degree Celsius change since 1980. And then if we start to project this forward into the future, of course, there's different models for different projections. This is all from NOAA. The top line curve is it takes into account, the red line takes about a 3% increase per year in greenhouse gases. The green is a balanced, basically doing what we're doing now. And then the blue line takes into account an increase until 2040, and then lowering it back down to 1990 levels by 2100. And so, you know, that keeps us under that 2 degrees Celsius that we hear a lot of people talking about as critical to limit the changes in our climate. So how is that affecting South Florida, in particular sea level rise? This is a graph from the Southeast Florida Climate Compact, and shows the different predictions of our sea level rise. Again, you know, kind of low, medium, high predictions. And we have our planning horizon. We see how it's been trending so far, right? The 5-year average down there at the bottom left, and then what it's going to look like going up. So if we look at our planning horizon, if we're just doing a building that we're thinking 50 years, we're talking about, you know, 2 to 3 feet kind of. And then if we're projecting out longer in that, say to 2100, we might be talking about 92 inches, maybe even as high as 136, which is, you know, quite an increase if you think about it. Our precipitation has also been getting more intense. This graph shows the trend in heavy precipitation. And the reason why that is because the water holding capacity of air increases about 4% for every 1 degree Fahrenheit in temperature warming. And that increases the water vapor in the atmosphere, increases the water vapor in the clouds and the storms. And then when we have rain events or tropical cyclones or hurricanes, those carry more water and they you know, rain more and produce more precipitation as they come down. If we take a look at, you know, where Miami sits in all of this, the trends are vary depending on where you are in location on the earth, right, on your latitude. And so, you know, Miami is closer to the equator, so we're going to receive a larger increase in that precipitation or in those precipitation events as we go forward. And that is also feeding into, you know, the trends in hurricanes. So these graphs here show the power distribution index, which is an aggregate of intensity, frequency, and duration of hurricanes that's measured over the course of the whole hurricane season. And we can see the trend here also since about 1980, right? You know, put a trend line to it. And we can see definitely that that power distribution index is increasing over time. You know, we just take that out into the future and we can kind of imagine what that is going to be like for us. And so the question becomes, you know, for us, architecture, engineering, and construction professionals, how should we built environment react to this? You know, what can we do in order to not only mitigate the short-term disruptions, right, but also the long-term impacts? And I think that that's where our 2 pillars come in. You know, the first one being resilience, which is the ability to recover and adjust easily to misfortune or change. And, you know, it's kind of short-term thinking in a sense, because we need to survive the storm in order to, you know, make sustainability last. And we almost need to have resilience in our buildings in order to have sustainability, because this isn't sustainable, right? What happened in Mexico Beach or the Bahamas or these other areas is really not sustainable. And there's a lot of people looking into this, not only on individual buildings, which this talk is really on, but also about how larger communities can adapt to this. We heard the mayor talk about they lost their police station, their fire station, you know, all these buildings, which, you know, devastates the whole community. And so, you know, how do we extend this to a larger urban planning context is being studied by a lot of people, and there's some good information coming out on that as well. And so if we switch now and look at the longer term implications, how do we reduce the long-term impacts? Well, we got to think about sustainability. And sustainability, you know, is fulfilling our own needs without compromising the ability of future generations to meet their needs. And so it really is kind of the, you know, long-term thinking in the fact of, you know, we need to have a sustainable economic, environmental, and social systems. I'm sure everybody has seen this graph, the triple bottom line of sustainability. You know, in this talk, we're going to be talking mostly about environment, a little bit about economic, and not so much about social. But, you know, we should keep all of those in mind. And the social probably extends more into that urban planning realm of having community buildings that are resilient, you know, and all of our services, all of our governmental services, and resilient type buildings. So how do we implement this, right? When you're we'll start with finished floor elevation, which really is probably more of a resilience thing, but can also be sustainability. Information that you got to collect right away as you're starting to look at a building design. You need to collect the elevations of your site, right? That would include the crown of the road elevation, the grade elevations around the building, right? The sidewalk elevations, and that's in order to see how your building is going to fit, you know, the finished floor or the elevation of your building is going to fit on that particular parcel of land. You also want to see what flood zone you're in. If you're in a, you know, a VE, AH, or AE, right, you're probably going to have dealing with the first requirement here, the base flood elevation. If you're in a flood zone X, more than likely you're not going to deal with that. You'll be dealing with the crown of the road or the 100-day storm or the 100-day 3-year storm stage. But, you know, in order to set that finished floor elevation, you know, these are the minimum requirements. And they vary by municipality. I think Miami Beach might be up to base flood elevation plus 2 feet. So there's some variation in this depending on where you are. But then if you just look at, you know, placing your building heights, right, you want to slope up 6 to 8 inches from the back of the sidewalk to get to the garage. And then you got to transition from your grade elevation up to the finished floor. If you need more than 3 steps in order to get up to that, you're going to be talking about having some kind of handrails, of course, in with those. If you get above 30 inches above your grade, you're going to have guardrails, which are just a higher handrail. With commercial projects, you got to worry about ramp distance and things, but that's not, you know, really required for residential. Some important adaptations that we're seeing with municipalities is that they're allowing us to start to measure our finished floor elevation, or the building height from the finished floor elevation. And so the building height has to do with the overall height of the structure. And they were getting a lot of resistance from industry because people didn't want to lose any height in their building if it was measured from the sidewalk or from the crown of the road. But now when they're adjusting those zoning requirements to measuring from the finished floor elevation, you know, that allows us to keep that, allows builders to keep that height that they need. So when we get onto the engineering and permitting of this, you just need to make sure that, you know, that finished floor elevations marked clearly on the site plan in NGVD or NAVD, and those are just 2 different ways to measure the height above sea level to keep it simple. And, you know, really you want to be in the 10 to 14 foot range NGVD for residential projects. And, you know, you might be 8, 9, 10 feet in a different flood zone, in one of the flood zones, the AE flood zone. But if you keep between 10 and 14 feet, you're going to keep ahead of that curve, that sea level rise curve that we saw a little bit earlier, you know, the 2 to let's say 4 feet in the 75-year time horizon. And you're kind of keeping ahead of the curve as far as, you know, those rising sea levels and your protection against the storm surge and stuff. Of course, when you get, you know, closer to the water, right, you got waterfront property, it's more complicated, but then you're probably in an AV or something type zone, and you got to look a little closer at those finished floor elevations. In construction, the surveyor will come out and mark that height somewhere on your site, usually with a pin. In this case, it was on a pole, might be in a tree or somewhere else. And then your shell contractor, of course, needs to match that elevation of the floor with that pin. And then you can make sure that you got all of your heights set, and then all the heights of the building are going to be measured off of that. So when we're looking at the structural shell, we advocated and went with an all concrete and concrete masonry unit shell, and it's preferable because of safety and lifespan. And the reason why that is because it makes for a stronger structure for wind mitigation. It has a rigid, what's called a rigid diaphragm if we're talking about structural engineering. And when we talk about the diaphragm action, I don't want to get too technical, but really what that is just a way that the forces are transferred, the lateral wind forces are transferred throughout the building and down into the ground. And that rigid diaphragm of a concrete structure is much stronger than a wood one. And so it also allows for parapets, not that, you know, wood trusses don't allow for parapets, they do, you can do parapets with wood trusses, but they're just a little bit easier with all concrete. And those parapets are a better design option because they in essence protect the roof. They protect the roof from those wind forces. And they also, if you choose to do solar panels, which we did, you protect your solar panels. So you kind of get multiple benefits from it. So a trend in all concrete construction is to use fiber reinforced polymer rebar, which is a great option. We did not use that on this particular house. And the reason was because at the time, which was 2016, 2017, when we were going into permitting, we really didn't feel that it was that well accepted, both in the permitting offices and in construction. Finding the people to build with the FRP rebar was going to be difficult and probably cost prohibitive for us at least. But we are currently working on projects that use FRP reinforcement. And we see in the last 5 years that technology and the acceptance of that technology has just really come a long way. So we're looking forward to that. In engineering and permitting, the all concrete structures are looked very favorably upon by the building reviewers and the building officials, precisely because they know that they're stronger and they can withstand those wind forces a lot better. And other than that, you just need to do, kind of your typical South Florida structural plans and calculations and go through the typical kind of permitting process that you would normally for a project. During construction, we did some interesting things. We put a little bit of a camber, which is moving the structure up a little bit to counteract the deflection on the poured in place concrete where the cantilever was, because we had a nice cantilever, about a 10-foot cantilever off the back. We did an upturned beam in an area to keep the inside space clear. I got a little picture here of me and my son doing a rebar inspection on the roof. And so here we also see the clear story that sticks up above the roof area. That clear story is used for stack effect ventilation. So it's kind of one of these aggregated benefits that we talk about incorporating. And I'll come back to that stack effect ventilation a little bit later when we're talking about energy. So one thing I should mention is the economics of this. It is more expensive. You're probably talking 20% more expensive on the shell of the project. That's the enclosure. One benefit of it economically, though, is that it does qualify for what's called a superior construction type for your homeowner's insurance. And so, interestingly enough, the homeowner's insurance on this house is actually cheaper than was on our previous house, specifically because we qualified for that superior type construction on the insurance. So you got a little long-term cost savings by building a superior type structure. Moving on to water reduction measures, right? So first, we're going to try to look at how we reduce our water usage and then, kind of produce our own water. It's interesting that, I always thought it was interesting and didn't really realize that about 30% of water use is used for landscaping purposes. And so, we really wanted to focus on the reduction of the use of water for landscaping. And to do that, we looked at a couple of resources. One of them is the University of Florida Load Maintenance Landscape Plants for South Florida, which was very helpful. And we also took a look at the Miami-Dade Landscape Manual in order to, select our plants for going around the house. We also included low flow fixtures, which is a requirement of Miami-Dade County now, and including two-button flush water closets and low flow fixtures for showers and kitchen sinks. Here's a table that comes from the Miami-Dade Water Use Efficiency Manual. And if we see here, if you do that, which is required now, you save about 31% of water use in your property, in your house. And so, by implementing that, that was a key water reduction strategy in of itself. So during the construction, you got to make sure that you select the right fixtures, right? Get the fixtures installed correctly. And then also when the subcontractor is installing the landscaping, double checking to make sure that, those are the right species of plants that are getting installed that are that respect on the plants. So now the water harvesting, right? What you can get from the rainfall. Miami is weird because it has, two different seasons, the wet season and the dry season, as we all know. And so although Miami, we get plenty of rainfall, 62 inches annually, average rainfall, which, is plenty of rainfall, it's really divided into two seasons. So storage capacity really becomes an issue with harvesting and storing the water for the dry season. With this comes challenges. Right away, you got to ask yourself, do we want to do a gray water system or do we want to do a black water system? Do we want to do a net zero water system, which is out there, which, you know, you can recycle some of the water within the house, the gray water or the black water. And all gray water or black water is, you know, either the water that's coming out of your faucets, washing machine, or the black water, which is coming out of your toilets. And, you know, you could purify that to different extents. Our decision for residential was that no, that, you know, really wasn't cost effective for us. And so we decided to stay focused on the rainwater collection for the landscaping. And so we did the calculation though of, you know, what our potential harvest was. It's, you know, something you should always do while you're thinking about design is figure out how much you can harvest. And so from the roof, we could harvest about 64,000 gallons annually. And then you want to look and you want to try to compare that to, you know, what your demand is going to be. So the average home uses about 300 gallons a day. And with our 31% reduction, our demand ended up at about 76,000 gallons. And so we couldn't really harvest enough water to be net zero, even if we wanted to, without recycling some. Unless we also looked at some of the hardscape outside of the building, which, you know, to us, again, that we just thought that that was cost prohibitive. So we decided not to do that. When you look at how you're going to harvest the water that you do harvest though, you got to pay attention to the roof slopes, what direction they're sloping, how you're going to get those into gutters and ultimately down into the cisterns. And then we had you know, placed 2 cisterns along, I guess you'd say the back side, the utility side of the house, the west side of the house. And those cisterns look like this. We made sure that they had spouts where we could connect hoses to them. And, you know, made sure that, you know, the downspouts and things line up with them. So you can come down and have some kind of filtration. We just have a net for that. But I do have to say that we are working on some future projects where we have built-in cisterns. Those built-in cisterns will allow for the capacity in order to use harvested water, you know, even into the dry season, really reducing the, you know, the demand on the well or on the city water. So now we're going to start to take a look at the energy and envelope of the project, and that includes the insulation. And so one of the things that we do right away with any project is we do a solar study. This is part of the building information modeling that I was talking about earlier. And let me just bring up a of the solar study that we can take a look at. Initially study how the sun goes over the building. And you can see, you know, you can do this for any time of day, any day of the year within the program. And so what you're really looking for is a couple things. You're looking for how, excuse me, you're looking for the eyebrows in the front, right? So you see here, you're studying how that sun interacts with the eyebrows and how those eyebrows cover the openings, the window openings or door openings, because you want to have those protected from the sun, especially on the southern exposure, southern and western exposure. You're also studying daylighting because daylighting, right, is key to reducing the use of artificial light. It's also good for health and wellness, right? How people feel on the inside of the building when they're using it. And in a Miami type environment, you want to have indirect daylighting. You want to avoid any of the direct sunlight that you can. And so, you know, the eyebrows and things that we place around the building are really to allow for that indirect lighting as opposed to that direct lighting. So then we start to study we start to gather some of the information on the insulation requirements, right? Energy.gov is a good resource for this. They list the different insulation recommendations for the different climates. You can see we're in the #1 zone down here. And on the walls, we decided to go with just a typical type foil insulation for South Florida. We did that understanding that really the roof is the key part of the heat gain into the building. And so we decided to just go with kind of a standard insulation on the walls, but we did decide to go with a high performance insulation on the roof, sprayed on closed cell insulation, 4 to 5 inches of it, which gets us in the 30 to 35 range of R value, which is just the resistance of the heat flow from the inside to the outside. One good thing about that spray-on insulation is that it also works as a moisture barrier. So it helps to limit the infiltration and the, you know, the kind of the moisture penetration into the house as well. So it's kind of another one of these aggregated benefits. And then when we're doing the permitting, the engineering and the permitting, you know, this is a wall section. On the wall section, you just got to make sure to get the insulation in the right spot and show what the values are. So there's the ceiling insulation, the wall insulation. And we also chose to do a cavity wall on the south facade. The cavity wall is done by putting another wythe of masonry outside the existing wythe or the primary structural wythe. So if you look here, you have kind of the CMU and the structure, and then outside of that, we put stone, partially for the performance, the energy performance, and partially because we like the look of it. The keystone makes it really feel like a South Florida home, and we like natural materials. And that also limits the transition or the transmission by conduction of that heat through the wall. We have about an inch air gap between those two pieces of masonry or thermal mass, and that really limits that heat transfer from the southern exposure onto the inside of the house. In construction, that insulation gets a little tricky. It's more intense to install. It's a spray-on process, so you need to get the installer that has the hazmat suit. Takes a little bit longer, costs, you know, maybe 10 to 15% more than regular insulation. And so, you know, there are some complications with the construction side of it. You also need to get light fixtures that are okay to have insulation sprayed around them. They're called IC light fixtures. And that's just a special UL rating that you'd have to get on those light fixtures. So here we have a picture of the outside. Remember the study of the eyebrows, right? So you can see the shading devices are working as they were planned in the building information modeling tools. And you also see that stone wall on the southern exposure, that cavity wall, which if you look behind that cavity wall, you'd see about an inch air gap behind that separates it from the masonry wall, you know, stopping that heat transfer from that sun going through the wall. So now we want to talk a little bit about energy reduction. So with energy reduction, key is really benchmarking to a certain level that you want to hit. So this chart shows our energy use intensity factors. Energy use intensity is a measure of how much energy a building uses over the course of a year. So if we look at the units, the metric units are on the top and the English units are on the bottom. The metric units are kilowatt hours and meters squared per year. English units, kBTUs per square foot per year. So it's a measure of energy per size of building, right? Per square meter, per square foot. For this presentation, I'm going to stick with the metric units just because usually we measure energy in kilowatt hours or kilowatts. So I've kind of translated everything into that, but this shows all the different uses of buildings from vacant, you know, to food service, kind of ranked as far as how much energy they use. And what I've done is I've superimposed some residential targets on top of this. So the American Society of Heating and Refrigeration Engineers kind of has a baseline. It's called 90.1, and that would be the baseline. This is the average single family home that's been built between 2000 and 2015. And then if we take a look at, you know, some of our future targets, which includes the Architecture 2030 challenge or goal, that would be, you know, down here. And, you know, we're going to talk a little bit more and put some numbers on these, but this is just, you know, visually you can see how as we're moving forward through time, you know, we're wanting to reduce the amount of use of energy per square foot over the course of a year. And so when we, you know, started with our house, or you want to take a look at your house, you could just go to your energy bill. This is the FPL dashboard from your house. Anybody can go on FPL and get this information. And when we went and we did the math and we figured it out over the course of a year per square foot or square meter in this case, we got about 125, right? Which if we go back, that's in line, you know, basically with what an average, you know, single family home is doing. And so then we started talking about, well, if this is where we're at, where do we want to be in the future, right? If we're going to build a new house, where do we want to be? And so we started looking at some more of the definitions. And some of the definitions for a high performance house was 77.8 kilowatt hours per meter squared per year. And so we said, well, for sure we want to be considered a high performance house. And this is just on the energy reduction measures, right? This doesn't have to do with, you know, any energy that we're going to produce on site. We want to look at first reducing our amount of energy that we're using. And we also used our building information modeling tools, our energy modeling in particular, in order to take a look at the house. So in the energy modeling tools, what this allows you to do is it allows you to change different design decisions and look at how those impact the energy usage of your house. So you can change the orientation of the house. You can change the insulation levels on the roof, on the walls. You can change the overhangs. You can change the window sizes. You can change, you know, a lot of the different components with the building, and you can run different iterations of that design and then get the energy use levels that you're going to have. And so you can see on here on the tool, it gives you your benchmarks, your 90.1, the 2030 challenge, even though the 2030 challenge also takes into fact production on site, which we're going to talk about next. So when all said and done, we said, okay, well, let's shoot for a goal of 65 kilowatt hours per meter squared per year, right? As an operating, what we'll call an operating energy use intensity, right? And that doesn't include any production that we have. It just includes what we're going to be using with the operation of the house. And so, you know, that was less than that high performance building that we wanted to get to. So then we started talking about, well, how does the architecture impact this? Well, the placement of the spaces impacts this, because the placement of the space is related to the fenestration or the window openings. So our lot was orientated, the long direction was north and south. And if you look at, you know, kind of traditional sustainable design, you want a long east-west axis to your building, and you want the windows to face north and south so you can block them from the sun. We really didn't have that option because our lot was long in the north-south direction and narrow in the east-west direction. And so what we tried to do to mitigate this was we put the private spaces that really don't take windows or take very few windows on the south and the west, because those are the more intense sides for the sun, for the heat, including the office, carport, kitchen, laundry, bathrooms. And then we put the more public spaces on the north and the east, right? Where we want to get that glass and that glazing and get the natural daylighting, the indirect daylight into the interior spaces, so we don't have to use artificial light. Those are also the spaces that people, you know, are using during the day, right? So we want to have those spaces well lit with natural light. On the second floor, same thing. Bathrooms. I mean, at some point, you know, you got to have some bedrooms on there, but you know, bathrooms, closets, and things, you know, mostly with smaller windows aligned towards the west, particularly, and the south. We also wanted to incorporate natural ventilation, and in order to do this, we incorporated a design for the stack effect. The stack effect is just that heat rises, that air rises when it gets hotter, and it's natural for thermodynamics that it does that. And so we have a double height space over the main space, and what that does is it allows for that heat to rise up in that space when it gets hot and then be exhausted out windows at the top. And we can see that a little bit better if we look at the building section here. This is a section now looking through that space with the double height space, and you can see the windows at the top. We did hook some electric low voltage motors to those windows so we can operate those windows and let that hot air out. And, you know, we don't do this year round because sometimes in the summer months, it just, you know, it's not practical and it just doesn't work with that hot. But in the winter, it does work very well. We've used it many times, and it does cool the house off given certain temperature and air conditions outside. So other things that we did, you know, as we've seen the glass on the different sides, we also decided to place the equipment on the roof. You know, putting the equipment on the roof keeps it out of any possible flooding, you know, from rain, even though we were in flood zone X. So, you know, we really didn't have to worry too much about that, but we did place the equipment on the roof for resiliency reasons. So we used what is a heat pump water heater. We at first spec'd a GE brand, but it was discontinued, and Rheem is one that we ended up going with. And actually, they got a great video out that explains it much better than I probably can. So I'll just play the video here for you guys. It explains how the heat works.
Introducing the new Rheem Hybrid Electric Water Heater. With a uniform energy factor of 3.55 to 3.70, this is the smartest and most efficient water heater on the market today. It can save homeowners up to $4,750 in energy costs, and it's the quietest hybrid on the market at 49 decibels. Plus, the Rheem Hybrid is compatible with the EcoNet smart monitoring system.
Oh, having a little technical difficulty.
Offering Wi-Fi connected control both at home and away. Here's how it works. A fan pulls air through the upper enclosure of the heat pump. The air passes through a filter to remove any debris or dust. Heat in the air is absorbed by the eco-friendly refrigerant inside the evaporator coil, and cool, dehumidified air is exhausted. Refrigerant is pumped by a compressor through the refrigerant system. The compressor increases the temperature of the refrigerant, which is delivered to the condenser. The condenser tubing is wrapped around the water heater tank where heat is transferred from the refrigerant to the water. All functions are controlled simultaneously by an advanced control. In energy saver mode,
So I'm going to stop it there. I think that's kind of, the basics of it. I think the key is that, this is another one of those sustainability measures that you get aggregated benefits. You get hot water, which uses a lot less energy to heat, and you get cold air. So it reduces the amount of energy that your mechanical system needs to use in order to cool the air. And so, it was really a great measure to introduce. On the mechanical system side, we had two systems, one upstairs and one downstairs, kind of in the private spaces and the public spaces. We chose to go with what's called a two-stage system over a variable speed system, just really due to cost, and we thought it was the best value. And what that two-stage and variable means is it's in reference to the fan speed. So you can be at a high fan speed or a low fan speed. That's the dual stage, right? The lower fan speed obviously uses less energy. And with a variable speed, it just allows it to kind of vary throughout all those different speeds. But we ended up going with a SEER 17 or 18, 17 to 18, I think it was 17.8 unit in our house. And so another part of the energy transfer into the house is the windows. Really, you measure that through the solar heat gain coefficient and the U values. We're getting these also from energy.gov, these recommended values. And we decided to go with a standard product with a low E, what's called a low E coating. And that low E coating gave us a solar gain heat coefficient of 0.25 and a U value of 1.07, which are, I would say, average, right? It's not high. You can go with like multi-pane glass windows. We didn't do that. We did a single pane. And it seemed to work out all right. It was probably the right balance between sustainability and cost. And then in the permitting, you just have to do kind of your permitting drawings that you would normally do anyway. One thing about the clear story was the motor specs, right? So we went and we spec that motor. This is just the type it is. It's a low voltage. You can use them for skylights or for clear story windows, and it just operates that window, in order to open and close it without having to get up there because they're so high up in the building. With the water heater is a little bit more complex than a typical water heater. It has an extra condensate line that you got to direct outside. It's got an inlet and an outlet that you would need to put on your mechanical drawings if you chose to do that. As far as the windows, you got to look, double check the specs that you're getting for the windows. Make sure that it's got that low E coating, that you're meeting your U factors and your solar heat gain coefficient targets that you set out for your windows and doors. And then of course you got to double check everything, make sure that it works. With that, I have just window that we were checking during commissioning of the building, making sure that that works. Here, this is the mixer, and that opens and closes the windows. We do have energy sensors with these. We hadn't installed those yet, but that is something that we'll get to in the future. Kind of a future improvement.
Precision Dog, a name you can trust.
Sorry about that. Let me get back on track here. We're here. And sorry about that. So now we're on to the energy production. Energy production has been simplified by the National Renewable Energy Laboratory. They put out this nice chart. This chart shows, basically what your peak sun hours are per day. And really what that is they just take the curve of how you get solar radiation and they kind of square it off into a nice usable block that is counted in hours or half hours or quarter hours. And then you can use that to get the number of, or the potential that you have at your house or on your roof over the course of the year. So if you wanted to calculate the potential that you have at your house, you would just take the number of panels that you can fit on your roof, the panel wattage, and you multiply it by the solar hours per year. And that's going to get you your potential harvest, your potential solar harvest in energy over the course of a year. And you want to go and you want to balance that with your demand. And as we mentioned before, we set a design goal of 65 kilowatt hours per meter squared per year. And so in order to calculate, that demand, you would just take that energy use intensity of your building and multiply it by the square feet or square meters, and you get that in your kilowatt hours per year. And you could also go, if you have an existing house, you could go to your electric bill and take a look at how much energy you used in the last year, and then take that as your demand value. And then to get the number of panels, you can just set those two things equal to each other and calculate and solve it for how many panels you need. And you get your number of panels. We calculated 35.6. We got 36 panels installed. Actually, at first I thought we were only going to get 34 based on how much room we had on the roof, but we ended up getting 36, which was a happy surprise. So that was the good news from the solar subcontractor. The bad news from the solar subcontractor was that those panels were only going to produce 15,000 kilowatt hours over the course of the year, where we thought it was going to produce 19 or 19,500. So automatically we kind of took a hit on that, and it put a dent in our hopes of becoming a net zero house. So, we moved forward through the process and tried to maximize the amount of solar potential we had and, minimize our use as much as possible. But that was really due partially because of the solar panels we chose. We chose a Solar World product because they're made in the USA, and they had a little bit less than a production than we had assumed at the beginning. On the engineering with the concrete shell, one of the aggregated benefits is that, the solar panel connection is much simpler than it is with a traditional truss roof. The penetrations of the membrane and everything is much simpler. Other things you need to look out for is, running those wires inside of the house. So you want to run those down inside of the walls somewhere so they're not seen. The other option with people that install, maybe in an existing house is they end up with conduit running down the outside of the house. And that doesn't, look too great. And so on the construction side, here's the solar panels, one of the arrays installed. You can see it here, right, kind of protected by the parapets, okay? And then the solar panels also protect the roof. So this slide shows the energy production of the panels over the course of a year. You can see that it's higher in the summer, lower in the winter, as you would suspect. And this is the panel layout. The panel layout also shows how many kilowatt hours, each panel produces. We use micro inverters on each one. And so through the Enphase online app, you can monitor the production of the panels. And as you can see, the production of the panels was pretty close to what the solar subcontractor had quoted us on. And so I think they said 15 megawatt hours, and we're at 14.9 megawatt hours. So very, very close. And now, so looking at the actual performance of the building, here is the first year or the last year of our energy usage at the house. We knew that we weren't net zero just because we were getting bills every month But you know, I really wanted to figure out, because we want to look at the operation of this and try to improve our operation over time. And so, you know, you can take a look here at what our average monthly usage is. This is from the FPL dashboard. And if we take the FPL information and combine it with the solar information, we end up at about 21,600 kilowatt hours of energy used for the whole year. That includes what we produce ourselves. And so basically our operating energy intensity was about 73. That's still less than the 77.8 that is the definition for a high performance building, but not down to the 65 that we, you know, had hoped that we were going to go with, that we were going to get based on what we were doing. Now this could be a lot of different reasons, you know, thermostat settings, COVID, right? Because we've been in the house for school and everything else as well, you know, using the house all day long, where I think, you know, typical projections of energy uses don't consider that people are in the house during the day. So there's all kinds of those variations, but, you know, we're happy to see that we still met the definition of a high performance building with how we were performing. And then if we start to include the solar production, we get down to 22.7, which is below the architecture 2030 target. Which we were also happy to see. Of course, we want to get down to zero, right? So we're a net zero energy building, but we haven't quite gotten down there yet. And so, you know, in the future, we hope to get to those goals of the net zero energy building, which is how we originally had intended to design it. So how are we going to get there? Future improvements. We do have Nest programmable thermostats. I've tried to incorporate those. Seems like people are always messing with the thermostat when the temperature goes up. And so trying to instill a little bit of lifestyle change, I guess, within the family members in order to keep that temperature so it goes up in the middle of the day and then comes back down at night. We also want to install the temperature sensors at the windows at the top for the clear story. So when certain temperatures happen up at the top, they can open up, let that hot air out, and then close. I think that would increase the performance. Simple as just increasing the indoor air temperature. You know, usually we got the thermostat pegged at 75. I think if we move that up to 77, we'd probably be doing a lot more as far as energy savings. And I'm sure that would bring our energy usage down. I mentioned about COVID, you know, just the higher use of the house, people being around. And we could use, you know, the EUI of schools to try to offset that, or maybe try to equate that a little bit to see where we'd be, you know, using that type of EUI instead of an EUI of a house. One thing that I would like to really do is do some smart home automation with algorithms. For instance, you know, maybe those temperature sensors at the top, along with, you know, knowing what way the wind is blowing and the temperature outside, could activate those windows or activate the mechanical system to you know, turn on or off. I'd really like to investigate that. I think that'd be very interesting. I think there's some commercial products out there, Davios and some other ones that might add to that. Batteries are still not really cost competitive. I've priced out batteries a couple times and they're still pretty expensive for what you get. You know, from what I saw, even the last round a couple months ago, you'd still be better off buying a regular traditional generator than doing the batteries. And then, of course, lifestyle change, right? I think that's the big question for everybody. There's always this kind of thing that you gotta suffer a little bit in order to be green. We haven't really had any lifestyle change in our house yet, so maybe that would help reduce our energy usage. On the bottom is a link to some pages in a book that our house is featured in. It was noticed by this publisher, not necessarily for its sustainability features, but more for how it looks and how it functions. And so if you're interested, I invite you to go down and check out that link. Another house that we also designed in Miami is on that link as well. So when does the price come due? I guess that's the big question that we had at the beginning, right? Is it this year, this next year, you know, within the next 5 years, the next 10 years? You know, when are we going to start to build in a resilient and sustainable way that, you know, that allows us both to bounce back quickly after a storm, but also in order to reduce those impacts over a long period of time and to get our climate so it's functioning normally? I think it's going to take some upfront investment, although you can see by like payback period on solar panels and other things that, you know, over time, that money is usually more economically sustainable, but I think that means that you got to be invested over the long period. And so some of our development models, you know, build and sell right away, don't necessarily meet those kind of goals. And, you know, so maybe we got to start experimenting around with some different delivery models, some different procurement processes that might, you know, want to invest more for the long haul to instill those resiliency and sustainability measures into the built environment. So we should all, I'll just close with the last picture and say thank you. And, you know, hopefully being part of the Green U and part of the University of Miami, we can all lead by doing. So thank you for your time. Thanks for coming. Hope you all got a little bit out of this that you could take home and use in your everyday life and maybe even in your professional life too. So with that, we'll take some questions. Hopefully we can patch that in, Teddy, and that'll work. Let me know if we need anything else.